Hello everyone, we are QuantYantriki, and our hack for the Quantum Science and Technology Hackathon is based on using feedback assistance in quantum annealing for hedging and portfolio optimization. The goal here is to make the solutions returned by the quantum processors more reliable and more optimal, in addition to exploiting the potential quantum speedups in portfolio optimization. This relates to the financial services theme in the hackathon. So when we create a portfolio, we choose certain stocks from possible asset choices shown here in green and drop certain others shown here in red. The risk associated with that portfolio is the variance of the return. One wants to minimize that. Hedging is a technique of minimizing the risk associated with a portfolio. Mathematically, it's the expectation value of certain allocation vectors with respect to the covariance matrix, which is based on historical pricing data of the assets that we can choose from. The allocation vector is a bit string where 1 represents a particular stock that we choose and 0 represents any stock that we drop. Uh, of course, any portfolio has to be designed with respect to certain constraints like a cost constraint, the total budget allowed for that portfolio. The technique of hedging involves choosing stocks in our portfolio which are negatively correlated so that any price increase of one is matched by a price decrease of the other so that the variance of the return is limited. This mathematical problem of risk minimization, if performed classically, can be inefficient because the number of possible allocation vectors grows exponentially with the number of asset choices. However, one can formulate this risk minimization procedure as an energy minimization procedure, and then we can use quantum fluctuations to explore the energy versus configuration landscape such that quantum fluctuations can help us jump out of local energy minimum traps and find the true global minimum. This quantum speedup can achieve via either a quantum annealer or a gate-based quantum approximate optimization algorithm. However, in both cases, one wants the solutions to be optimal and reliable. This is where feedback can come in. In feedback, what we do is we compare the portfolio projections from model one, say, which is based only on covariance, with partial information that can come from some other model, such as simulations or machine learning. The relative confidence that we have on these two models can be expressed in terms of some threshold probability. And we compare the entries where the two predictions don't match. So here S3 is predicted to be picked by model 1 and S3 is predicted to be dropped by model 2. And we would make a choice based on the threshold that we set. The quantum subroutine runs iteratively, and at each at the end of each iteration, we check statistically for matches on the entries that we know. Whenever the entries don't completely match, we provide feedback to the quantum subroutine based on this amount of on the model threshold. If the marginal probability of the return solutions by the quantum subroutine is greater than the threshold, then we accept that as the final solution. In terms of an actual algorithm, this heuristic can be implemented using both a quantum annealer or a quantum approximate optimization method. The input is in the form of the covariance matrix and the cost constraints, which are fed to the quantum processing units in terms of a qubit interaction matrix and the local fields. In every iteration, the output is a distribution over possible solutions, which are compared with the partial prediction of the alternate models, and they are tested for convergence. If that is not met, the local fields are adjusted and the quantum subroutine is run again. This continues till convergence is reached, and the final recommendation is in the form of a optimally hedged or balanced allocation vector. The improvement due to feedback is achieved in terms of the distance of the return solutions from the optimal solution and also the variance of the return solutions. The final output will have a sharper and narrower peak and will also be closer to the optimal solution. We will now show how feedback-based hedging is performed both in the quantum annealing model and the gate-based quantum approximate optimization method. The end user just needs to use a web-based interface, which we now explain. So the end user interacts with what we call the minimum risk portfolio generator. This basically supplies user input to the quantum computational subroutines at its backend. Depending on the level of user access, these subroutines can run the algorithms on actual quantum hardware or on local simulators. So in order to design a portfolio, we can choose from a certain selection of stocks, and we can provide a date range over which the covariance matrix is to be calculated. In principle, the number of stocks or assets one can choose is unlimited. However, in this demo, we'll limit it to a maximum of 10 so that we can actually implement it on quantum hardware and compare both the QAOA, the quantum approximate optimization algorithms, and the quantum annealing algorithms under feedback. So here we show in green the user making a certain selection of stocks. Setting the date range. And so with the choice of the assets and the date range, the covariance matrix for model 1 is fully specified. When it comes to model 2, which is the alternate model, which can supply us partial information about the optimal portfolio, there are two modes for the user to input this information. One is to use the automatic prediction that the user interface provides. The other is to use the manual prediction mode. So essentially here, all the twos represent the fact that we do not have enough information to either choose or drop a stock. Choosing a stock would correspond to setting it to a 1, and dropping a stock would correspond to setting it to a 0 value in the portfolio allocation vector. The user can then choose a relative measure of confidence between the two models. So by setting this to a value of 1, for example, the user would say that the portfolio allocation vector must necessarily match all the partial asset choices that have been provided via model 2. By setting it to 0, the user is suggesting to the computational subroutine that model 1 is to be relied over model 2 completely. The user then enters the budget, and the budget should have enough space for non-trivial solutions. Setting it to a very low value would basically mean that we cannot choose too many stocks at all. And then once all these inputs are provided, both the models are fully specified, and then one can choose whether to use quantum annealing for the computational subroutine or to use the gate model for the computational subroutine. The final output is in the form of a recommended minimum risk allocation. Here, all the zeros represent the fact that the computation process suggests that we should not be picking these stocks. The green ones imply that we should be picking those stocks. The yellow one is confirmation that the predictions from model 1 and model 2 match as they should because of the feedback process.
Hi. So now we know how the user interface works. So I'll talk about the backend. From the user interface, we are receiving the following: the covariance matrix, the current prices, the total price, the total price or the budget, partial data, which we'll also refer to as the model 2, and probability of convergence. So let me briefly talk about the binary quadratic model that we have implemented in our code. So the objective function looks like E of x is equal to summation jij xij xij. So this term, the first term, basically shows the coupling between the ith and jth components of the vector x, and the second linear term represents the biases. So hi's over here represent the local fields or the biases. We can calculate the jij and hi using the covariance and price constraint. So we minimize e of x at each iterate and at each iteration, and we provide feedback by updating hi based on statistical checks compared to model 2 data. So this process is continued till we uh, reach convergence. Next, let me talk about quantum annealing. So this is a process in which quantum fluctuations are used to explore the entire search space. So what happens here is we have a Hamiltonian, a time-dependent Hamiltonian h of t, which can be expressed in the form a of t hp plus b of t hp. So hb is the mixing Hamiltonian and hp is the problem Hamiltonian. Their forms are shown here. The time-dependent coefficients a of t and b of t vary in this way, which is shown in this figure. So it is clear that after a sufficiently long time, that is after the annealing time, what happens is h of t basically converges to h of p. So at the final time, the solution is encoded in the ground state of the problem Hamiltonian. Now let me talk a little bit about simulated annealing. So simulated annealing method is a very powerful classical method. So we have used this method for our prototype. So what happens here is random points are generated based on a probability distribution at a particular iteration. So what happens is, suppose pi is the correct point and current point, and p new is the random new point. So what we do is we compare the old and new objectives. If the new objective is better, we make p new as the next point, and if not, we feed the solution into an acceptance function, and if the acceptance function basically returns a yes, what we do is we once again make p new our next function, and this has a non-zero probability. Whereas if it returns no, pi plus 1 becomes pi, that is the previous current point gets carried forward to the next iterate. So that is how it works, and this process gets continued.
Hi, I will be introducing you to the quantum approximate optimization algorithm, commonly known as the QAOA, implemented using the gate model of quantum computation. On your screen is a 3-qubit circuit diagram. Each of these qubits corresponds to one stock in your portfolio. There are a series of gates that are implemented. I'll walk you through each of them and their purpose. The first gate is a Z rotation gate by delta. This is a single qubit gate. It corresponds to the feedback you're given to the stock. Say, currently the recommendation is a 1 and you wish to change it to a 0. I.e. currently you're recommended to purchase a stock and you do not wish to purchase that stock. You will be giving it a positive rotation. On the other hand, say if currently you are not purchasing a stock, but you wish to purchase that stock, you'll be giving it a negative rotation. The next set of gates are the ZZ coupled rotation by gamma. These are the blue 2-qubit gates that sandwich a purple single qubit gate. These gates encode the covariance or the correlation between any two stocks in your portfolio. Finally, we come to the single qubit X rotation. These act on every qubit and ensure that you're exploring the complete solution space so that you can arrive at an optimal solution. This entire array of gates on your screen corresponds to one time step. This algorithm approximates an optimal solution by doing several iterations of this over multiple time steps. Currently, we are working with an order of 100 time steps. At the end of all of these 100 time steps, we measure each of these qubits onto a classical register, which means that we are going to be getting a 0 or a 1 as a recommendation for every qubit or every stock in our portfolio. We do this measurement for this entire circuit multiple times. After a couple of thousand measurements, we plot the probabilities and we plot the statistics, and then take the least energetic or the most optimal states that have been recommended, compare them with the future solution or the user constrained solution, and then implement another feedback routine. This feedback is then fed back into each of these qubits, and the circuit is iterated over and over again until we have arrived at a single optimal solution that minimizes the cost, minimizes the risk, and maximizes the profit. Thank you.
So to summarize, we have created a minimum risk portfolio generator application that uses a classical quantum hybrid algorithm to implement feedback assisted quantum computation for portfolio optimization. This can potentially exploit quantum speedups in the risk minimization process while increasing the reliability and optimality of the return solutions from the quantum hardware. Thank you for your attention.